1C, we will be looking at the energy. So we will recall the terms that we know, such as relative atomic mass, relative molecular mass, molar mass. We will look at calculations from moles. We will look at the Avogadro's constant and different ways to write up a chemical equation and calculate the reacting masses. Here you might be expected to find the mass of or mass of any particular reactant if the other reactant is given, how much is required to react completely with the first reactant. You will be expected to calculate percentage yield and percentage uh, atom economies. Now, all of the prior information you have already gone through for your O levels. The new thing here is percentage atom economy. So these few slides will give you the definition of MR, AR, so relative molecular masses, relative formula mass, then molar mass. All these definitions are here, which you already know. And then you have Avogadro's constant, which is 6 into 10 to the power 23 per mole. And this is the Avogadro's triangle. So to find number of particles, we have to multiply number of moles with the Avogadro number, and the number of moles can easily be found by um, this equation where number of moles equals to mass in gram divided by molar mass. There are many worked examples available in the book. Feel free to look at the worked examples from the book. Now, to calculate reacting masses, 4 steps need to be followed. First, you need a balanced chemical equation. Then you have to determine the number of moles of the known substance. Next, you will use the molar ratio according to the chemical reaction and then find the mass of the unknown substance. So here is an example. I will show one example here. So firstly, the question is asking us calculate the mass of calcium oxide formed from 25 gram of calcium carbonate when it is decomposed. As you can see, calcium carbonate decomposes to calcium oxide and carbon dioxide. We have the information already given for one substance, which is calcium carbonate, which is 25 gram. So we will divide it with the MR of calcium carbonate, which is 100. So 25 divided by 100, we get 0.25 moles. So this is the known substance. Step 1 was writing the equation. Step 2 was calculating the number of moles of the known substance. Now in step 3, you will look at the mole ratio. Here the mole ratio is 1 is to 1. 1 mole of calcium carbonate will give rise to 1 mole of calcium oxide. That means 0.25 moles of calcium carbonate will give rise to 0.25 moles of calcium oxide. Now, in the fourth step, to calculate the mass of the unknown substance, you just have to multiply the number of moles with the MR of that substance, which in this case is 56 for calcium oxide, and the answer comes out to be 14. Here is another example which you can take a look at. Same thing and same few steps are followed. The only difference in this equation is that the molar ratio is 1 is to 2 because you're finding the water molecules ratio, and the known substance given is methane, which has the ratio with water of 1 is to 2. So whatever answer you got in step 2, that will be multiplied with 2 to get the number of moles of water, and the rest is going to be as before. Here are more worked examples of similar calculations. Next thing that you need to know, excess calculation. This means that if 2 reagents are given and you have to find which one was in excess and which one was the limiting reagent. So here also you have to follow a few steps. This is a very systematic way of doing these kind of calculations. First, you will look at both the reactants only. You will not be looking at the products. You will look at both the reactants and their mole ratio. As you can see, copper is reacting with nitric acid. So copper is to nitric acid is 1 is to 4. So this is the mole ratio written 1 is to 4. And for each of them, you will be given a particular amount given. In this case, number of moles have to be found out for both the reactants. So for copper, mass is given 3.2. You divide it with the AR, you can get 0.05 moles of copper. For nitric acid, fortunately, you're already provided with the number of moles. If you did not have the number of moles initially mentioned in the question, you would have to find it separately. Once you have the number of moles, you can check with the molar ratio which one is in excess. So you have 0.05 and 0.4, and you need, according to the molar ratio, 0.05 moles for copper. You will be needing 0.2 moles of nitric acid. So it is visible from this how you have more nitric acid. So nitric acid is in excess, and on the other hand, your copper is the limiting reagent. For percentage yield, you can use this formula where actual yield divided by theoretical yield with and the whole thing will be multiplied with 100 to find the percentage yield. You have more worked examples shown here also. You can do the calculation stepwise. Atom economy is a new term. This just gives you a ratio between the mass of the desired product and the mass of all the products formed. So for example, if any particular reaction has only one product at the end, we can say that the atom economy of that particular reaction will be 100% because it makes no byproducts and you get 100% of the desired product. But if there are additional additional products present, then the atom economy will decrease. So the formula of atom economy is stated here: molar mass of the desired product divided by sum of the molar masses of all the products times 100. So we can make a few generalizations about these reactions, that addition reactions, since they have only one product, they will have 100% atom economy. Elimination and substitution reactions will have lower atom economy. Multi-step reactions will have even lower atom economies. Some examples are mentioned. These are all worked examples from the book. This is from page number 25, so you can take a look at this worked example. Formula, which is in 1D, and in 1E we have calculations with solutions and gases. So for the first portion, calculation with masses, it's the same thing. You can find out the ratio, and from that ratio you can find the empirical formula. So to find empirical formula, you will be either provided with the masses, and as you can see, this is also done stepwise. So you have the mass of copper and of oxygen. You divide it with their relative atomic masses respectively. So copper has a relative atomic mass of 63.5. Use that value. So 3.43 divided by 63.5, you're going to get 0.0540. And for oxygen, you have 0.85 grams divided by 16, which is the relative atomic mass of oxygen. You will get 0.0531. Now divide both of them with the lowest value. So you are going to approximately get a ratio of 1:1. Therefore, the empirical formula for this compound will be Cu2. We can also find the empirical formula using the percentages. If the percentages are provided, then it is great, but if sometimes in a compound there are three elements present and you have the percentages of only two, and the third one can be found out by subtracting the previous two from 100. So the procedure stays the same. You will be dividing each of these elements with their relative atomic mass. After doing that, you will find which value is the lowest. Here 1.6 is the lowest value. You will divide all of them with 1.6 and you can get the ratio. So the answer stands C2H3Cl. This is a similar type of calculation. As I was mentioning here, the percentage of oxygen was not mentioned, hence it was calculated separately to be 30.4 after subtraction of the other two elements from 100. If you look here, after finding the smallest number and dividing it with all of it, the ratio comes out to be 1 is to 1 is to 1.5. In this case, multiply all of them with 2. If you have any value with zero point 0.5, multiply all of them with 2. You can easily get rid of the zero point 0.5. So the 1.5 becomes 3, and the other elements will have a ratio of 2. So the final empirical formula stands Na2S2O3. Here also you have worked examples mentioned, so you can take a look at those. Now, those were prior topics you have seen before. Now, this is an equation for an ideal gas. You can see that it is given as PV equals to nRT. You need to understand what each of these represent. P represents pressure and it will be given in Pascal. V is the volume, which will be given in cubic centimeters. If you have it in cm cube, you must convert it into meter cube. N is the number of moles. R is called the gas constant, and the value will be provided in the data booklet. You don't need to memorize it, but the value is still given here, which is 8.31 joule per mole per Kelvin. And lastly, T is temperature, and it should be in Kelvin. So always make sure that they are according to their SI units in the question. Not all the time you will be getting the question with the correct SI units. You must convert them accordingly and carry out your calculations. As you can see, worked example 3 from your book, pressure was given in kilopascal, it was converted into Pascal. Volume was given in cm cube, it was converted into meter cube. Temperature was given in degrees Celsius, it was converted into Kelvin before you could carry out your calculations. Next, you have calculations involving molar volume. This is also prior knowledge from O levels. When you are finding the volume, you have to uh, understand that what the formula is. You have already done it before. Volume is equals to amount in mole, and then it will be multiplied with your molar gas volume. So your molar gas volume can be in dm cube, that is 24, and if it is in cm cube, it should be 24,000. Examples of that are mentioned here. So if you have any gas being formed, and in that case, you have to find the number of moles of the gas first and then multiply it with 24 to find the volume of that gas. Next, we will look at mass concentration. This is different from the molar concentration that we are familiar with, because the molar concentration has a unit of mole per dm cube, but this one has an unit of gram per dm cube. You can see the expression for finding out mass concentration in gram per dm cube. It is the mass of the solute in gram divided by the volume of the solution in dm cube. And accordingly, your examples are provided on the slides. You can take a look at them. As you can see in this figure, the color becomes deeper as the concentration increases. Now, it was easier for us to see the color and deduce that the right beaker contains the most concentrated solution and the left beaker contains the least concentrated solution, but most solutions that we deal with are not colored. So that is why this is not a very good way of understanding which one is more concentrated or not. So we have to carry out other analysis and find that out. Another unit of concentration that we will be using, and that is new to your that is new from your prior knowledge, it's parts per million. In short, we call it ppm, and the formula is given below. Concentration in ppm is equals to mass of solute times 1, and there should be 6 zeros as it is called parts per million. So in million, there are 6 zeros. So mass of solute times 1 million divided by mass of solvent. Here you have your worked example provided as well to help you understand that ppm can be found for liquids and also for gases. They are sometimes found to find the amount of pollutants that are present in a particular sample. It could be from air, or it can also be from a water sample or a solution sample. In worked example 4, for example, we can see that we have nitrogen dioxide gas, and with a volume of 1.5 dm cube, it mixes with um, a particular amount of air, and we can find it by using the previous formula. Volume of the gas should be on the top, that means the numerator, and it mixes with air. Air's volume should be in the denominator, and you should have that 1 million multiplied with the numerator. You will get the answer 150 ppm. The unit here is ppm, parts per million. And then you have practice questions that you can do from the end of the topic. Thank you, students. That was all for topic 1.